Welcome back to AI.Code.Cast. Today we're going to be diving into a real brain teaser, a coding problem that pops up a lot in technical interviews and also has applications in fields like natural language processing.
Yeah, it's a classic challenge that really makes you think about efficiency and how you structure your data. We'll be exploring how to find all the concatenated words in a given dictionary.
Okay, hold on a second. Before we get too far into the weeds, can we just define concatenated word? What does that even mean?
Absolutely. So think about it like this. You have a dictionary with words like cat, dog, and bird. A concatenated word is any word that you can make by just stringing together two or more words from that dictionary.
Got it. So bird cat would be a concatenated word if our dictionary is just cat, dog, and bird.
You got it. And the challenge is, if we have a dictionary, how do we find all the concatenated words?
This sounds pretty simple at first, but I can already see how it could get really tricky with a really big dictionary. So where do we even begin with something like this?
Well, let's start by thinking like how we would solve this without any fancy algorithms.
Oh, yeah.
Like if we were just trying to solve this ourselves without knowing all these computer science techniques.
Okay, so like brute force. I guess we could just go through each word in the dictionary and see if we can break it down into smaller words from the dictionary.
That's exactly right. That's totally a valid approach. It would definitely work. But the problem is, what if the dictionary has thousands of words or even millions of words?
Yeah. That would take forever.
Exactly. The brute force approach just isn't efficient enough for big dictionaries, so we need a smarter approach.
Okay, so brute force is out. So what are some better ways to solve this? The source material mentioned dynamic programming and a trie-based approach.
Those are both great options, and they both rely on this idea of solving smaller subproblems.
Okay, interesting. So instead of looking at the whole word at once, we try to build it up piece by piece.
Exactly, like building with Legos.
Got it.
And that's where dynamic programming is really helpful.
Okay, so dynamic programming, what is that exactly?
It's this idea that we can use the solutions to smaller subproblems to build up to the solution of the big problem.
I'm not sure I'm following completely.
So think about climbing a staircase. Every step you take is like a prefix of the word. And if you can get to that step, it means you've made a valid concatenation up to that point.
Okay, I can kind of see it.
Yeah. So then the question is, how do we actually keep track of whether we can reach each step?
Yeah, how do we do that?
That's where the dynamic part comes in. We can use an array, often called DP, and each element in that array tells us if we can get to that step.
So like, if DP5 is true, that means we can build the first 5 letters of the word from our dictionary.
Exactly. It's like a checklist to keep track of which prefixes we can build.
Got it. Okay, that's cool.
Right.
But how do we actually build this array? How do we fill it in?
That's where we get into the programming part of dynamic programming. So we start by initializing every element in the array to false. And then the very first entry, DP0, we set that to true because an empty string is always a valid concatenation.
Right, an empty string. That makes sense.
Yeah. So now we have our starting point. So what do we do next?
So we've got our starting point and we have this array that's mostly false.
Exactly. So then we look at each position in the word. So let's say position I. And we want to see if we can get to that step. So we look at all the previous positions.
All the previous positions before I.
Yes. From 0 all the way up to I1.
So we're basically saying, can we build the prefix up to I from any of the prefixes we already know are valid?
Exactly. You got it.
Nice.
And then for each of those previous positions...
You mean like position J?
Right. For each J, we check 2 things. First, can we reach J? So is DPJ true?
Okay, so is that prefix valid?
Right. And second, is the substring from J plus 1 to I a valid word in our dictionary?
I see. So if we can get to J, A, and D, the rest of that substring is a word in the dictionary.
Yeah.
Then we know we can get to position I.
Exactly.
And then we can mark DPI as true.
Exactly.
So we're basically taking 2 valid pieces and sticking them together to make a bigger valid piece.
That's a great way to put it. And then we just keep doing that for every single position in the word.
Okay, I like it.
Yeah. And then at the very end, if the last element in the DP array is true, you know, the one that represents the entire word, then we know the whole word is a valid concatenation.
This is so clever.
Yeah.
But this must take up a lot of memory, right? That DP array could get huge for a long word.
Yeah, you're definitely right. There is a trade-off here. Dynamic programming is really fast. But it could potentially use a lot of memory. But before we get into the memory stuff, let's take a look at a different approach, one that uses this really cool data structure called a trie.
Okay, yeah, tries always seemed kind of mysterious to me. Let's dive into that. Okay, so tries. I remember learning about those back in school, but I could definitely use a refresher. How would you explain a try to like someone who's never heard of it before?
Imagine you have a huge library with tons and tons of books, and you want to find all the books that start with compute, like computer or computation or whatever. A try is like a special index for words that helps you find them really fast.
Okay, so it's kind of like a really efficient search tree for words.
Exactly. Think about like an old phone book, where you flip to the C section and then the O section and so on. A try works kind of like that.
So each node is a letter, and a path through the try is like a word or a prefix of a word.
Right.
Okay, so that makes sense. But how do we actually make a try from a dictionary? Like for this concatenated words problem.
Okay, so let's say we have a dictionary with the words cat, cats, and dog. We start with an empty root node. That represents the start of any word. And then for each word, we add its letters one by one as new branches.
Okay, so like for cat, we would make a branch for C from the root, then a branch for A from the C node, and then finally a T from the A node.
Exactly. And since cat is a valid word, we would mark that final T node in some special way so that we know it's a word and not just a prefix.
I see. And if we added cats, we would just add an S to the T that's already there. We would make a whole new path.
Yeah, exactly. That's one of the great things about tries. They're really good at storing words with common prefixes.
Okay, so cat and cats share that same prefix
Right. And then dog would just start a new branch from the root.
with a D at the beginning.
Yeah.
Okay, cool. So now we've got our try. How do we actually use this thing to find concatenated words?
This is where depth first search comes in.
Ah, okay. Depth first search or DFS.
Yeah, we can use DFS to explore all the possible ways to split a word into smaller words.
Okay, walk me through an example.
Okay, so let's say we're looking at the word cats, dog, cats. We start at the root of the try, and we look at the first letter C, and we ask, is there a C branch coming from the root?
And there is. So you go down that branch,
Exactly.
and then down the A branch, and then the T branch.
Yep.
Okay, so now we're at cat.
And we have a choice. Do we stop there because cat is a word? Or do we keep going to see if there's a longer prefix?
Okay, so we could keep going down the try.
Mm.
Or we could say, hey, cat is a word. Let's make a note of that.
Yeah, exactly.
Okay, so we found our first potential word, brick.
That's a good way to think about it. So now, this is where the DFS part happens. We basically start a new search. But this time, starting from the T node.
The chi at the end of cat.
Yeah.
So we're basically asking, can we build the rest of the word stogcats from words in our try?
Exactly. We're exploring all the possibilities, all the different ways we can split up that word.
And if at some point we hit a prefix that's not in our try, like SEST,
Yeah.
then we know that path is a dead end. We don't have to waste time going down that path.
Yeah, exactly. That's what's so cool about tries. We can avoid all those bad paths, and that makes the search so much faster.
So we only go down the paths that have potential.
Nice. So what happens if we search all the paths and we don't find a way to split the word into dictionary words?
Well, then we know the word isn't a concatenated word. It can't be built from our dictionary.
Okay, so the try and the DFS together are like a really smart filter.
Exactly.
They quickly help us figure out which words are concatenated and which ones aren't.
Yeah, it's a really powerful combination.
Good.
And I bet this idea of using a try to search for prefixes, it's got to be useful for other things too.
Oh, yeah, definitely. Like, you know how when you're typing in Google, it suggests words for you?
Yeah, autocomplete.
Exactly. That's often powered by a try. And things like spell checkers, too.
Cool. Okay, so now we've talked about dynamic programming. We've talked about tries and DFS. They both solve the same problem. But they both have pros and cons. So how do we decide which one to use? So when we're looking at this concatenated words problem, trying to decide between dynamic programming and the trie-based approach, what are like the big things to think about?
Yeah, that's a really good question. And it kind of comes down to these classic trade-offs in computer science, like time versus space and how complicated things are.
Okay, so those classic trade-offs. Let's start with time complexity. How do they compare in terms of how long it takes to run?
Dynamic programming is usually really efficient in terms of time. It kind of builds up the solution step by step and avoids doing the same work over and over again. So in the worst case scenario, it has a time complexity of big O of n times m squared, where n is the length of the word we're checking, and m is the maximum length of any word in the dictionary.
Okay, so n times m squared. And what about the try with DFS? I feel like that one is harder to figure out because of all the recursive calls.
Yeah, that's true. Like in the worst possible case, DFS could end up being exponential. Like, if there are tons of ways to split the word, we might end up going down a lot of different paths in the try. But in reality,
Mhm.
it's usually much faster than that because we can often stop searching early.
Right, because if we hit a prefix that's not in the try, we know we can stop. We don't have to waste time going down that path.
Yeah, exactly.
Okay, so the try saves us time, but what about memory?
Yeah.
Doesn't the try take up a lot of space, especially if we have a big dictionary?
Yeah, you're right. That's the trade-off with tries. They're great for searching for prefixes, but they can use a lot of memory. The amount of memory they use depends on how many different prefixes are in our dictionary.
So if I had like a massive dictionary with tons of words, and memory was a big concern, I should probably just stick with dynamic programming.
Probably, yeah. Dynamic programming gives you pretty good performance, and the code is usually simpler.
Okay, that makes sense. If I had plenty of memory to spare, and I really needed the fastest possible solution, then the try approach would probably be the way to go.
Exactly. It really depends on what your priorities are,
That's a good lesson in general for computer science. It's all about understanding the trade-offs.
for sure.
Cool. So we've seen two different ways to solve this problem.
Hmm.
Two pretty clever ways.
Yeah, and there might be other cool ways to solve it too, depending on what you're trying to do.
That's what I love about coding. There are always multiple ways to do things.
Definitely.
Well, I think that wraps up this deep dive into concatenated words. I hope our listeners learned something new today.
Yeah, me too.
So to all our listeners out there, try implementing these solutions yourselves. Play around with different dictionaries and see what happens. Maybe you can even come up with your own clever variations.
Yeah, and if you do come up with something cool, be sure to share it on our community forum.
We love to see what you all are working on.
And thanks for listening to AI Codecast.
Happy coding!